Welcome to the second talk on Riemann-Hilbert problems, nonlinear Riemann-Hilbert problems. And for those who could not attend the first part, I will give a brief summary. Here's an outline of what we will discuss now in the afternoon session. So first of all, we have a short summary of the first talk. Then these Riemann-Hilbert problems will be related to extremal problems, which are very familiar in the case of conformal mapping. And these principles can be extended to Riemann-Hilbert problems. Then I give an application to filter design, and finally I will talk on nonlinear transmission problems. This is the type of Riemann-Hilbert problem which correspond to this transmission problem where we have a jump function and we are looking for a holomorphic function or sometimes for two functions which are coupled across the common boundary of the domains. So first of all, a short summary of this morning. Bernhard Riemann was interested in his thesis in well-posed boundary problems for holomorphic functions in some domain. We restrict ourselves to the unit disk, and he came up with the following setting. We are looking for holomorphic functions W in the complex unit disk, which extend continuously to its closure, such that they satisfy a boundary condition of this type. F of t, W of t is equal to 0 for all t on the unit circle. Here this function f is a given function which lives on the product of the circle with the complex plane and has real values. So we have one condition, one real condition at each point for 2 degrees of freedom of this complex function. So half of the boundary values are prescribed in some sense. So then it is convenient to look at this problem from a geometric point of view. So we introduce the target curves and restate the problem. Here we have the target curves and we rewrite the problem in this way. So this means we are looking for these functions W such that W maps corresponding boundary, maps a boundary point here onto the corresponding target curve MT1, and this for all points. We can lift this tangle of target curves to the product of T with the complex plane, and then we get an object which we call the target manifold of the problem. So all boundary conditions are encoded geometrically in this target manifold. And the solution is just a line on this target manifold. More precisely, we consider the graph of the boundary function of a solution, and then this is a line on this target manifold. The standard example is this modulus problem, or say this standard modulus problem, where we are interested in all holomorphic functions having unimodular boundary values. This is a torus-like target manifold, and more generally we call such torus-like target manifolds admissible if they are given by such a parametrization, which basically means that all target curves are closed, smooth, and depend smoothly on the parameter t in the boundary point t. Then we have solutions with different binding numbers about this target manifold. And now we have a very important assumption which will be discussed later in this talk, namely we assume that the origin is contained in the interior of all target curves. Then this binding number corresponds to the number of zeros inside. This is just the argument principle. And we can generalize this a bit. We call this target manifold regular. if there exists a holomorphic function bounded and continues on the closed disk, which takes values at t, which are in the interior of this target curve mt. This is just a matter of shifting functions. And this is the main result. For all torus-like, say admissible torus-like regular target manifolds, we get this nice holomorphic parametrization of the target manifold. So the target manifold is covered by the traces of solutions with winding number 0, which I also call the fundamental solutions in a schlicht manner. So every point on this target curve, we have exactly one trace of a solution. Okay, and we have other solutions. I will skip this here. So now we all know that conformal mapping or conformal mappings are characterized by extremal principles, by extremal properties. And there are even proofs of the Riemann mapping theorem which rely on such extremal principles. And it's a natural question to ask if something similar holds for Riemann-Hilbert problems. To achieve this goal, we are considering now a new set of holomorphic functions. Contrary to the first part of the talk, we do not assume that these functions are continuous on the closed disk. They are just bounded in the interior. So this is the Hardy space H infinity. We have bounded holomorphic functions. One is known from Fatou's theorem. Wow. Is that these functions have non-tangential limits almost everywhere on the boundary circle. So it makes sense to speak about boundary values of such functions, though they are not continuous on the closed disk. So, and what we do is we take the boundary values and restrict each boundary value to the interior of this corresponding target curve. Okay? And this should hold almost everywhere on the unit circle. So there's a well-known special case. If all target curves are unit circles, then this set A is just the closed unit ball of H infinity. Okay? But this is a reasonable set. And yeah, we try to explore this set A. Here I have tried to visualize the set A. You see a piece of the target manifold, which is cut here, that we can look inside. And inside we see traces of 4 functions which belong to this set A. These are tame functions which we see here. They are really continuous up to the boundary, but there are also wild animals living inside. Okay, so this is the set A. And now when we restrict the boundary values of such a bounded holomorphic function to some set, and all these sets lie inside some disk, say, then it's clear that also values at interior points have some restrictions. So, for example, if we have all the target curves unit circles, then the restriction on the induced restriction on the interior values at interior points is the same. This is just a consequence of the maximum principle. Okay? And now the main question is, if we have restrictions along the boundary, which restrictions are induced at inner points? Okay? So we pick a point Z, say the origin here, inside the disk, and consider all values of functions in A at this point. At this point. Okay? This is some well-defined set. And the question is, how does it look like? Okay, can you guess it? So, and of course, we are interested in extreme functions which attain values at the boundary of this range of values. It is not clear from the beginning that such functions exist at all. I mean, this set could be an open set somehow, and that the no values at the boundary are attained. But the question is interesting. And here's the answer. We assume that our target manifold is a regular compact target manifold, so it's torus-like target manifold, and we pick any point Z in the unit disk. Then the range of values at this point is homeomorphic to a closed disk. Already nice. No restriction about the shape of these target curves. They need not be convex also. Can have arbitrary shape. Moreover, the extremal functions, which take on values at the boundary of this range of values at a fixed point, are exactly the solutions to the Riemann-Hilbert problem with winding number 0. So I think this is kind of intuitive. So if you pick a point in the disk and try to find values which are extremal, then also the values of the extremal function on the unit circle should be kind of extremal. If they all would lie inside the target curve, then we could move it around a bit. The main point is that they must be on the boundary everywhere. So we have a complete characterization of the extremal functions. They coincide with these fundamental solutions of the Riemann-Hilbert problem. If we go back to this standard setting where we have the real torus, the proper torus, then the solutions to the Riemann-Hilbert problem are just the constant functions. So, well, this can be seen immediately. Then all these ranges of values are also closed disks. And if a function attains a value on the boundary, modulus 1 in the interior, then it must have modulus 1 everywhere, and it must even be a constant. So this is an extension. And moreover, we have taken an arbitrary point in the beginning. If we would take another point, then we would get exactly the same set of extremal functions. It does not depend on the choice of this interior point. So as I said, this is the maximum principle in the standard case. We can also characterize solutions with arbitrary binding numbers. So for instance, if we take solutions with binding number 1, then we can prescribe an additional interpolation condition. And in the standard case, it makes sense, for instance, to require that the function attains value 0 at the origin. So what are the solutions in this case? The solutions to the Riemann-Hilbert problem. The solution to the Riemann-Hilbert problem are constants times Z. So now the theorem tells us that these are also the extremal functions. And if you translated this general result to this situation, then we see that we get the Schwarz lemma. Namely, for all functions which are bounded this way in modulus by 1 on the circle. We have W of Z modulus is less than modulus of Z. And if equality is attained at some point Z, it must be a function of this type. So what do we have to do if, to find the ranges of values? These can even be computed. Namely, we consider the corresponding Riemann-Hilbert problem. This can be solved, for instance, by numerical methods. We evaluate the values of the solution at the point, say at the origin. This yields a curve, and we have to fill in this curve, and this is the range of values which we are looking for. Okay. Now, the proof of this extremal principle is quite long. And if you are interested in these things, I would really like to encourage you to think about a better proof. So the proof has 3 steps. First of all, we need the fundamental solution of the Riemann-Hilbert problem. Maybe this is the hard part. Then we need the existence of extremal functions. This is not that hard. This is pure geometric function theory, normal families, arguments, and yeah. So these extremal functions even exist under very much restrictive assumptions on the target manifold. But not so for the fundamental solutions of these Riemann-Hilbert problems. And then one can show that both families in fact coincide. So, and it would be very nice if someone has an idea to give a direct proof, starting from the extremal functions, and then to prove that these extremal functions satisfy the boundary conditions of the Riemann-Hilbert problem. I tried it, but I had no success. And I will not do it anymore.
Elias, if one would have the naive idea to just transform the target manifold into standard terms.
Well, I mean, this is related to what I say on the next section. It's not so easy.
Yeah, sure. That was my question.
This would immediately solve all problems and much more.
Yeah.
So, despite the fact that we have this nice parameterization, it is not clear how we can transform a general Riemann-Hilbert problem to the standard.
You can do it with the sections, but not with the...
Yes. So, this is exactly a reaction somehow to your question. In the standard case, we know that the ZA is the closed unit ball of the Hardy space H infinity. And there is a question if there is kind of a homeomorphism between this closed unit ball and our ZA. This would allow us to parameterize all solutions to the Riemann-Hilbert problems by functions in the closed unit ball B. And we immediately would not only get our continuous solutions, but also solutions corresponding to infinite Blaschke products, to singular inner functions, to a very strange thing. But it's not clear how to construct such an homeomorphism. A positive answer is known for Riemann-Hilbert problems with circular target curves. Yeah, and maybe I have time, not sure, to show you this very briefly, which means I have to go to the other talk. And we have Riemann-Hilbert problems with circular target curves. We get better results than for the general problems. Here we have two functions, function which describes the center and the function which describes the radius. And assuming that this problem is regular, then we can suppose that we satisfy this condition. And then we only need Hölder continuous. Given data, C and R, and we can get all the results which we had in the general case, but now in weaker assumptions. And one can ask, of course, such a circular Riemann-Hilbert problem is given already by 3 points on each circle. So the target manifold would be given by 3 special solutions. And this idea can be worked out. And the answer is, it is really possible to construct all solutions from 3 special solutions. Here's the answer. What we get is kind of a fibered Möbius transformation. Some would call this a nonlinear parametrization. We can construct explicitly 4 functions. This is an algebraic operation now. P, Q, R, and S, which are in H infinity and up to the boundary in this Hölder class, such that this fibered Möbius transformation is a homeomorphism between the finite Plaschke product and the solution set, and at the same time we get a homeomorphism between the unit ball, B, and the set A, which we have. So here we see such a configuration. This can be determined algebraically. We started with the 3 given solutions, and now we can compute all these solutions. And if we plug in a finite Plaschke product, then we get all continuous solution. If we plug in an inner function, then we get all bounded solution of the Riemann-Hilbert problem. Yeah, well, and we can construct these alternatively from only one solution, but then it's not algebraic. We have to apply a Hilbert transform. So now back to this slide we have. So a positive answer about the existence of such a canonical homeomorphism is given for circular target curves, but in general we have no idea how to construct it. So let's go one step further. So far we always had the condition that, say, the origin lies inside the target manifolds. What is happening when we forget about this condition? What can we expect? It turns out that things can change dramatically. This is our standard example which I have here. We have many solutions given by all finite Plaschke products. Now let's take another problem where the target curves all pass through the origin, but they go around in the wrong direction, so to say. If this point T moves in the positive direction, then the corresponding curves N and T move around in the negative direction. Then we have, of course, a trivial solution namely 0, constant 0. But this is the only solution we have. No other solution exists. This is an exercise for you in the afternoon. It's not hard to show. It's interesting to think a bit. This is related to the problem how the image of the unit circle under a holomorphic function can look like. Can it look like this? The answer is yes. Can it look like this? I take into account orientation. Answer is no. This is a contradiction to the argument principle. Can it look like this? Whatever orientation you choose, you always get points which are where the function goes around in the wrong direction. So this also cannot appear. So there are some strange type of restriction to these traces of solutions. And this is the reason why these torus-like Riemann-Hilbert problems split into 3 different classes. And these are prototypes of the 3 classes. If we make these circles still more eccentric and let them go around in the wrong direction, then we have no solution at all. And here's the answer to the general problem. If we consider all admissible torus-like target manifolds, this set will be denoted by n. Then we have 3 classes, disjoint classes, which together form this manifold, this set of manifolds M. In the regular class, we have the same result as for the standard problems, the regular problems, which we considered in the morning. We have many solutions, and we can, the set of solutions is indeed a manifold, and it has a dimension, real dimension 2n plus 1. No, it consists of several components, I would say. So, in the singular class, we have exactly 1 solution. And strangely, this has a negative binding number about this manifold. How is it possible? How can the binding number about this manifold be negative? Doesn't it contradict the argument principle? No, it doesn't, because now we count the binding number with respect to this manifold. And in some sense, the situation is such that this manifold goes around this solution in the wrong direction. So you can easily construct such a singular problem just by taking 1 function and wrap any manifold around this solution in the wrong direction. Then you get a singular problem. And there's a third class which I call void, because these problems have no solutions. So typical problems of the 3 classes we have just seen. And now comes the thing which is maybe most surprising of all. When we have Riemann-Hilbert problems, we always assume that our solutions are continuous. In the class in the class A, we allowed functions which are just bounded. And these can be wild guys. Nevertheless, if we are in the singular class, then we have just 1 function in A. And this function must automatically be continuous because it's a solution to the Riemann-Hilbert problem. This was most surprising for me. So we have a target manifold, and we admit all functions to this class A, and there's only 1 function inside this class, and this must be a continuous function. So, to say it the other way around, this I already explained. No. Say it the other way around. If we have at least 2 functions in A, 2 bounded functions in A, then we know we are in the regular class. And then we immediately have a rich manifold of solutions. Okay. So let's still go a step further. So far we considered individual problems with a given target manifold. But we can also consider parameter depending problems. So we have a family of target manifolds and we deform these target manifolds. What's happening? In order to study such deformations, we need a topology, and we equip this Zm of all admissible torus-like target manifolds with the Hausdorff distance. So this is just what one intuitively understands by distance of two geometric objects. We already know that this M is a disjoint union of these three sets: regular, singular, and void problems. What are the topological properties of these sets? It turns out that two of them are open. The set R and the set V is open. The set S is closed, and this is the common boundary of the two sets. And moreover, the union of these open sets here, R and V, is dense. R and V is dense in all of them. This means generic problems, if you pick a problem at random, then this belongs to R or V and not to S. There must be a good reason why it belongs to S. A good reason can occur when you consider a continuous path which starts in the class R, say, and ends here, and ends in the class V. Because this S is the common boundary, it has to cross this class S. There must be at least one parameter value where we have a manifold in the class S, in the singular class. Now let's see how it looks. This is a regular target manifold, and we see the family of fundamental solutions. Solutions with winding number 0 about this target manifold. Now we deform it. So, do you see what's going on? This is the limit, where we just cross the common boundary. Now we are in the singular, in the class of singular problems. And here we have a single solution, this red line, and this has the one winding number. It has winding number -1 about this target manifold.
Could you step through those deformations again?
Yeah. And you see how they converge. One can prove that they in fact converge uniformly on compact subsets. All solutions converge uniformly on compact subsets to this one singular solution. But because the winding number jumps, convergence cannot be uniform on the closed disk. So these solutions with winding number 0 stay close to the singular solution, except at one small part of the target manifold where they go around very fast to get the correct winding number 0, which they have to have. They cannot approximate the singular solution uniformly. Nevertheless, there's even uniform and not uniform convergence, but pointwise convergence almost everywhere on the boundary. So we just have a certain number of such loops. Okay. This is a very nice result. And it even has an application. And this application is in the design of dynamical systems, or if you like, in the design of filters. So here's the setting. We The problem is an H infinity optimization problem in the background. This is linear causal time invariant stable systems, which are just operators which map the space of L2 functions on the real line, a bounded linear operator which acts on L2 on the real line, such that it is time invariant, which means if you plug in a function which is 0 for negative t, then you get an answer which is also 0 for negative. This is causal. Sorry. I explained causal. I say it again. If you plug in a function which vanishes for negative t, then you get a response which is also 0 for negative t. This is causal. And time invariant means if you plug in a function and shift the input by some time, then the answer is also the shifted output. So, and these systems can be described. Every system can be described by a transfer function, which I denote by f. This is a bounded holomorphic function in the right half plane. And in fact, this is a one-to-one correspondence between the operators of this type and the bounded holomorphic functions in the right half plane. So what is of a special interest, this is the value of this transfer function on the imaginary axis, because this has an interpretation. This is called the frequency response function. When the system operates at an harmonic input with frequency omega, then the output is just the Laplace transform, I must say. The Laplace transform of the output is just the Laplace transform of the input multiplied by this transfer function. And this omega has the interpretation of a frequency, so that the modulus of this transfer function is the gain of a system which operates at this constant frequency omega. And the argument of this f is the phase shift, phase delay between output and input. And this is what one is interested in. So it's an interesting goal to construct a system which has a given frequency response, f0. So what is the obstacle? The obstacle is that this frequency response function is the boundary function of a holomorphic function. And this cannot be prescribed arbitrarily. So we must admit somehow some freedom. And now I explain an optimization problem which was introduced by William Helton in the 1980s. He has a very general setting in order to evaluate the performance of a system. So we have an ideal frequency response function which we would like, which is our goal. And we have a realizable frequency response function, and we have to estimate how good it is. And there are different ways to do it. Of course, one can just take the Euclidean distance between, so the distance in the complex plane for a fixed frequency, and then one can take the worst performance, so the sup of this distance over all frequencies. This is the standard way of doing it. So, but Helton had the idea that it would be much better to introduce a penalty function which estimates the performance of the system at each frequency individually and somehow arbitrarily. So look at this picture. We are talking about a fixed frequency now, and the optimal value of this transfer function of the frequency response is here in the middle. And green means that the penalty is very small. In the ideal case, it is 0. Then we matched this frequency response function perfectly. And now we can define level sets and measure the performance according to these level sets. So red means the system is bad, and this operates badly at this frequency, and green means it operates good. So now this is Halton's setting of the H-infinity optimization problem. We have the penalty function, and we define the performance of a system as the supremum of this penalty function over all frequencies. And the goal is to minimize this penalty. So we are interested in the optimal performance and all transfer functions which realize this optimal performance. And this is related to our sets A, which we had. Namely, the level sets of our performance function can be interpreted as target curves. Okay? And altogether they form a target manifold. So this is the target manifold which corresponds to some value of the penalty. And we are interested in functions which do better, or at least at this value of the given value of the penalty. So this means our function have to lie inside this target manifold. What we get is a family of functions here, family of functions A of P, which consists of all holomorphic functions, which have traces inside this target manifold for a given value of P. And now we have to shrink this target manifold as much as possible to get the optimal performance. Okay. This is Halton's optimization problem, reformulated in terms of these target manifolds. Here we see the family of target manifolds. It's a nested family, getting smaller and smaller the smaller the penalty is. So now an interesting problem to you. What do you think will the solutions, the functions W inside such a target manifold do when the cage is getting smaller? And it's
the extremal function from the not the void but the borderline set.
okay. Yeah, they try to use the full space, and what will the others do inside? Do they have a chance to stay inside or not? The answer is they all must go to the boundary. So this cage is rather big. They cannot use this space because of the restrictions which come basically from the argument.
The solution to the optimization problem is then the singular solution.
Yes, exactly this happens. So we start with a regular problem where we have something inside, and then we shrink it and shrink it, and if it is too small, then we are in this void set, which means we have to cross the singular case, and this is the solution. Okay, this is already the explanation. Here's the setting again. So we have admissible torus-like target manifolds. They have to form a nested family. And if this P is sufficiently large, then we are in the regular set. If it is sufficiently small, then we are in the void set. And yeah, we have a continuous path which starts, I should say the other way around, maybe in R and ends in V. And so there exists an optimal P where we are in this set S. So, and indeed, This is the result. We get, under these assumptions, we get a unique solution of this optimization problem. And the solutions of the optimization problem are in fact solutions of a singular Riemann-Hilbert problem, which means they have some regularity, and they have the same performance for all frequencies, because they lie on the boundary of this target manifold, so they have the same performance for all frequencies. And moreover, they have a negative, now it's a positive value here, but they have a negative winding number about this singular target manifold, which is expressed here with the derivative of this function, this penalty function f. This is the conjugate of the winding number. So, okay, this I already mentioned. And this is not only a theoretical result, it also allows one to construct numerical methods, because we do not need to solve an optimization problem, which is kind of related to inequalities, which are can be badly handled. So we have an equation, we have to solve a Riemann-Hilbert problem. We have to find the singular Riemann-Hilbert problem and its single solution. So let's look at an example. Here we have a low-pass filter, which means if we have low frequencies, the frequency response function is 1. These harmonic oscillations go through, and it is 0 for high frequencies. This is the ideal frequency response which we would like to have, and we define a penalty. This would be the standard thing. We measure the distance from the optimal value. But for instance, we can also admit that we have a large deviation in the phase shift and only a small deviation in modulus. This would also do. So this leads to the following family of target manifolds. Here the blue line, this is just a trace of the origin. They look a bit strange. Everything is now transferred from the right half plane to the unit disk. We have this small, or the strong restriction for high frequency, so it should be close to 0, and we have a large range for low frequencies. So here is an answer. This is the solution shown as a trace on the optimal target manifold. And here's another one. It doesn't look that bad. And this is an Nyquist plot here. We see the level sets of the penalty function, and we see the frequency response. This is the image of the imaginary axis under the frequency response. And here we have a Bode plot where we see the phase shift. So it goes down to almost minus p, and then it goes up again, and we have the gain, which is, I mean, the scaling is not correct. It's almost 1 here in this region, and it's almost 0 here. No, not almost 0, but it's relatively small. You see the distance from the origin. Okay. So do I still have time to show this last part?
For 10 minutes.
Maybe
minus a few minutes for questions.
Okay. So now we change the class of problems. So far we had boundary value problems, and now in the last part we consider these transmission problems. Now we have two functions, two unknown functions. And there's a general theme which is related to this problem. Namely, we have a given function on the unit circle a complex function. And we would like to represent it by boundary values of two functions, f plus and f minus, which are holomorphic inside the disk and outside the unit circle. Okay? So the simplest thing is the Ries decomposition. So we can write it as a sum of two such functions. This is just done by the Cauchy integral. So we get a minus there, but I have a plus. Also, this is Wiener-Hopf factorization. Here we have an additive representation. Here we have a multiplicative representation. And there we already need this index here as kind of a diagonal thing which reflects some binding numbers. And more generally, we can consider these Riemann-Hilbert transmission problems. We are still in the scalar case. So this capital G and small g are given functions on the circle. Okay, so what about nonlinear problems of this type? So we just take a given function g, which now depends again on two arguments. The t is on the unit circle, and the second argument lives in the complex plane. And we would like to find two functions, one holomorphic in the disk, one holomorphic in the exterior, such that they are coupled across the boundary by such a nonlinear condition. So it turns out that this is significantly more difficult, this problem. And the reason I briefly mentioned in the morning, namely if you linearize this problem, then you do not end up with a problem of this type here, but we also get the complex conjugate of the plus function. And there are no such nice results, no formulas which we can exploit. So it's more difficult.
Can you form a system?
In principle, yes, but it does not really help. Yeah, but still one can get something, and here you really see the relation between this holomorphic and anti-holomorphic part, which is encoded in the function g. Namely, we have this function g, which is not assumed to be holomorphic, and this has a derivative with respect to the second variable, which I denoted by Sept here, and it has the Cauchy-Riemann derivative with respect to Sept. And the point is that the part here, no, the analytic part has to be dominating. So forget about this function little g in the beginning. So this has to be dominating against the anti-analytic part. And this function g can be included, and this makes it a bit more general. But this is not the final word. So, and but it's still a result, and we call this an ellipticity condition. Surprisingly, somewhat later, we found a special problem of this type which is really relevant and which is interesting. And this we call a Blaschke decomposition. Then we will think of this standard Ries decomposition as somehow related to the Euclidean distance in the complex plane. When we work in the unit disk, it's more natural to use the hyperbolic or pseudo-hyperbolic distance. And the pseudo-hyperbolic distance is related to this complex pseudo-hyperbolic distance. So what if we replace this complex Euclidean distance by the complex pseudo-hyperbolic distance? Is that a similar decomposition? And it is. So now we have bounded holomorphic functions, which are bounded in modulus by 1. No other restriction, no regularity, nothing. And then this admits such a decomposition, which looks like a conformal automorphism of the disk in some sense, where both functions, the plus and the minus functions, are bounded holomorphic functions, and both are bounded in modulus by 1, so this fits in the hyperbolic setting, and that's a normalization condition at infinity. And if we have functions which are bounded in modulus, which are less than 1 in modulus, in the norm, so these are functions which really live in the hyperbolic setting, so the boundary does not belong to the hyperbolic disk, then this representation is also unique. Okay, and there is also a hyperbolic version of Parseval's equation, namely, this is the standard Parseval equation applied to this Ries decomposition, and there is a hyperbolic version of it, which looks like this. We introduce this energy here, again related to the values of f. They must be less than 1 in order to apply it, and then the energy of the inner and the outer function sum up to the energy of the given function. So, okay, that's it. This is just for fun. During the last years, we became interested in circle packing. Circle packing is kind of a discrete version of complex analysis, say of holomorphic functions of one variable. But basically, the idea is that a holomorphic function is a function which maps infinitesimally small circles to infinitesimal circles, not to ellipses. And another idea is, what if we replace these infinitesimal circles by real circles? So we can take such a structure, which is a packing of circles, which have some tangency relations, so the neighboring circles touch each other, and they are allowed to move, but they have to stay in contact to each other. So neighboring circles have to touch, to be tangent during this deformation set. And this is a discrete model of holomorphic functions. If you take two packings which have the same structure of tangencies, then one can be considered as the domain packing and the other one can be considered as a range packing. I haven't shown the domain packing here, but this is a range packing. And now you can formulate Riemann-Hilbert problems for such circle packings. Namely, that the boundary circles have to be tangent to a given family of target curves. Okay? And we modeled continuous Riemann-Hilbert problems with such circle packings. And we got completely surprising results. This is a solution to such a discrete Riemann-Hilbert problem. The red line you see here, this is the solution of the corresponding continuous Riemann-Hilbert problem. And the dots on this line are the points of tangency of these circles, the boundary circles, to these target curves. And it is surprising how accurate this approximation is. So the packing is not that large. And here you see real and imaginary part. Unfortunately, first we thought, well, this must be converted in kind of a nice theory, but it turned out that it is not that easy. So there are several obstacles, mainly coming from discretization effects and from the appearance of branch cuts, which can be modeled with circle packings, but all this is more difficult, and so we finally stopped this project. But it is still nice, and maybe I can show you while you are asking. I can show you a demonstration. Oh no, this is not the right one. Sorry. This is another demonstration. No, yeah, maybe I'll show it to you later. Thank you so much.
Well, we are almost over time, but I guess we might have time for one or two quick questions.
In your discussion of why the nonlinear Riemann-Hilbert is much harder, you introduced these derivatives, the d bar derivative and the d derivative. So is the theory of quasi-conformal mappings lurking underneath here? I mean, you have a condition which is rather like the Beltrami coefficient condition, that the size of the d bar should be uniformly less than the size of the d. So in that case, you can solve Beltrami, and maybe in the class of quasi-conformal solutions, do you get something that could then lead you to conformal extremal maps?
So, I mean, we even studied also Riemann-Hilbert problems for solutions of the Beltrami equation. And basically the results are similar, but we did not follow this further at some point because it is getting quite technical and one needs more restrictions. So, and I'm not sure if one can also model this last problem, this nonlinear transmission problem via quasi-conformal mappings. It may be, yes.
Other questions, comments? Well, if that's not the case, then let's thank Elias for those two very good results.